Okay, a big welcome to you for the overview of the entire Aerospace Operations and Engineering Management course, or Engineering and Operations Management, AER1601. So this is basically an overview of the whole course. So this sets the expectations of all the stuff that you're going to be learning in the course over the full semester. So this is it's basically designed around the modules. So module 0, orientation, that's this module. There's more reading because you need to read the syllabus, review the syllabus. And also give you a bunch of primers and some academic papers on the whole concept of running aerospace engineering and operations management. It's a specialty field. I want to say right up front that this course builds on all my other courses. So I have in the undergraduate, there's business process management, it's called integrated systems design. It goes into the nitty-gritty details of how you actually manage an enterprise through business processes. And then the other course is the organizational design course. So it's like a mini MBA. So it just teaches you strategic management, basically a strategic management course that teaches the principles of marketing, strategic thinking, strategic management, how you deal with the external environment in the company, how you design the internal environment, how you design a manufacturing organization, the service organization, the differences between them. So it focuses more on the general business. You call it more a general business administration course. So it orients you for general management thinking. Now then they get into the master's course, the specialty courses, management of innovation. So much of my work was done in aerospace industries, managing innovation and change. So actually having knowledge of operations in engineering, how you actually design aircraft, how the aircraft development process works, how the manufacturing process works. Well, my work was to help improve those processes. So in order to improve them, I had to understand them, but I also had to understand how you go about transforming a company, and we call that management of innovation and change. The change aspects, the political aspects, the social aspects. So in that course, I teach those principles. And then there's a course called Operations and Production Management for Manufacturing and Services. So it's the generic operations course that really teaches you the mechanics and principles of how you operate a bank or a hospital or a university or a manufacturing company. It is heavily biased toward manufacturing, I might add, simply because operations science, the science of operations management, was born out of manufacturing. That's where that whole body of knowledge was really fostered. Well, you could say it was fostered in the military, because operations, how the Roman Empire expanded, was purely military operations and economic systems and so on, and how to manage the city, but it's all operations. But the modern based on industrial engineering techniques would have been really fostered from the 1920s onwards with mass production in the United States. That was really when modern operations management body of knowledge was born. And then the other course is the Applied Innovation course, where you actually go into a company to use innovation techniques, so creative problem solving, decision making, team building, all those quote soft skills, which, as I keep saying, are the hard skills in the real world in industry. You learn to do those in a real industrial setting. So this course really builds on those courses, because in this course, it's ideal if you have some operational management and engineering management experience, at least theoretical, but preferably on the job. It would also help if you've learned the soft skills of being able to work in teams, being able to do presentations, being able to engage in conflict resolution, being able to solve problems using fishbone diagrams, a systematic problem solving process. In addition, it's also be good if you understood how to manage change, because you're actually going to work on real work with these aerospace companies, solving real problems for them. So you're going to deal with real people, and they're expecting you to give value. So also understanding business process flow and business process management and innovation itself, how do you take ideas and implement them, and make sure that, or teach them to implement them. So that's another aspect of this course. And the operational side, again, is the technicals. So I'm going to try to teach you, the main focus of this, it is 100% aerospace focused. It is 100% aerospace examples. So I won't be giving you examples from the newspaper industry, from the food industry, from the machine tool industry, because it's irrelevant. I use those examples in the general operations course, in the innovation course, etc. But in this particular course, it's all focused on aerospace. So there's 4 main parts to it. The aerospace environment. So again, I'm just giving you an orientation today. Well, Mod 1, we look at setting aerospace in context. And Mod 2, which means I'm going to just talk about some of the language that you would find in the aerospace industry. So if you're in a factory where they're making whole aircraft, you need to know what a fuselage is, you need to know what the wings are, you need to know what ailerons are, you need to know what the flaps, the empennage, the nose landing gear, and so on. You need to understand all these basic principles so that when you're speaking to people in these companies, at least you understand their language and you understand what components of the aircraft. We'll also talk about in that the sort of strategic drivers of the aerospace industry. Then we talk about the aerospace supply chain. It's a vast network of companies all across the planet. I mean, just to create a Boeing 777 or Airbus 380, etc., are companies from all over the world providing input to these giant companies, these what we call Tier 1 OEMs, original equipment manufacturers. And in Module 3, we talk about transformation, business transformation, the lean enterprise. Really a focus on the lean enterprise, which was driven by the need to transform the aerospace companies back in the night. Like all this stuff came out of the 1990s and 2000s and really began in the late 80s. And it was as a result, of course, of increasing global competition. As you know, that in the 1980s, the United States and 90s, the United States automotive industry was decimated by foreign competitors, especially from Japan. This is all old history now. Well, the same was starting to creep into the aerospace industry. At one time, the British, the Americans dominated the planet with aerospace, with the Germans close as well, Italians, others, Spanish a little bit more. But basically it was an Anglo-American domination of the whole marketplace at that time. And of course these guys don't want to lose their market share, so transformation had to happen, but the way they did it was going to be interesting in that they engaged the whole planet in working with them. It's still unfolding, I might add. And part 2 talks about, this is where we get more into the nitty-gritty operational processes, so engineering and product development. So how does that management system work? How does that process work? So many engineers are trained in universities to be sitting in cubicles doing like stress analysis calculations, or maybe designing a component of a wing, and maybe in 15 years they actually get to be chief engineer for the wing itself, and in another 10 years they get to be the integrator of the whole aircraft. And that's the technical side of it. But if you're choosing a management path where you're looking at if you choose a technical management path, you're still going to have to learn management. So this course will set you in good stead, but you're going to take many years before you actually, get into the very senior levels of management. Typically, vice presidents of engineering and so on are definitely well in their 40s. You might get the odd one that's in their 30s, but typically they're in their 40s. And most likely in their 50s and 60s even. Similarly so we're going to talk about the process. So I'll talk about the phase milestone process of aircraft. Specifically, I'll give examples from Bombardier, from Lockheed Martin, from Messier Dowdy, Bugatti, Safran now it's called. Talk about a program management office. What does it mean? How do you design it? That's something that only emerged about 25 years ago in the aerospace industry, where there was a defined body of knowledge, the PMP, the project management designation, but building a program management, because most defense companies have 4 and 5 programs. So McDonnell Douglas, now Boeing Aircraft Defense, has the F-18, the F-15, the Harrier program, and they've also acquired Hughes helicopters. So there's the Apache helicopter, which is a military program. That's another program. So who's managing all these programs? How do you go about managing all this complexity? Lockheed Martin, F-22, F-35, F-16, and many others, multiple drone programs. How do you manage all these? Bombardier Aerospace, regional aircraft, And propeller, jets plus the propeller, you have the Q400, Q300, you have the Challenger aircraft, you have different jets. These are all different programs. So how do you manage? What's a program management office? So we'll talk about that. Then actually how do you initiate and execute a program? Part 3 is we move to manufacturing. Aerospace Enterprise Management Systems, also known as ERP. These are all software packages that integrate all aspects of the enterprise. We'll talk about that. And then product data. How do you manage the product data all the way through a program? So you've got the concept design, preliminary design, detailed design, then you build it, then you test it. All the information has been generated all the way through the life cycle of a product. How do you capture all that data, make sense of it and use it? So there's software out there called product data management, PDM systems, and the whole idea is to manage information for the life cycle of an aircraft so that you can make the right decisions in terms of its cost, its production, plus the reporting to the regulation authorities and so on. You've got the data there to back up decisions that you make and so on, and also back up your safety processes that you create. And then manufacturing planning, control and execution. Well, this is all about also known as MRP, manufacturing resource planning. So it's how do you schedule a factory? How do you know you have the right capacity? When do you make capacity decisions? Where's your inventory? What inventory do you need? How do you get the inventory to the line? And then when you get the inventory to the line, is it fit for purpose? It has to be. So the quality system kicks in. Then you've got labor reporting. So when they're building the line of an aircraft and they're building in the different bays, the wing, the fuselage, and then the integration of it, then the testing, all of that has to be controlled, and all of it requires labor feedback in order to determine what the costs are. Part 4 is aerospace regulation, culture and innovation. The reason I put this together is because the fact it's a highly regulated industry drives its culture. So there are many companies you go into a newspaper company. I mean, it's very important in a newspaper that you get your paper the next day. I mean, it's all paper, newspapers are a dying business, but the principle will illustrate it. Very rare would you ever open the Globe and Mail and see a big streak of ink down the middle of the page. That's by intent, obviously. You'd be angry if all your pages were smudged and your words were smudged. That's all a credit to that company's production processes, especially its print plant and so on, how they're handled, how the ink dries, and the mechanics and the physics of ink on paper and so on, and the printing process itself. These are all thought through years and years of chemical engineering. And so in terms of that industry, there's some regulation, but it doesn't impact life. So if you do get a big streak of ink down your paper, you're angry, but it's not going to impact your life. So the newspaper industry is not highly regulated, but aircraft is enormously regulated. And you'll see, I think it's 1 in 10 million. They anticipate 1 in 10 million failures. That's the kind of accepted failure rate in terms of an aircraft flying. It might be even more than that, but it's seriously among the safest industries that you can have. And I always want to touch wood, because when you're up on a plane, you have absolutely no control. The control is out of your hands. But it's highly, highly regulated, and it creates a very regulated culture. Engineers that work in that culture are very precise. They think precisely. The metrology labs where they do the inspection of the inspection equipment, so the inspection of the inspection equipment, are highly, highly disciplined people. They think plus and minus tenths of a thousandth of an inch. That culture permeates the whole of the aerospace culture, including the operators, the shop floor trades and so on, the riveters, and they're highly concerned about excellence in the work that they do. In my first year in the training school, I had to repair, or sorry, it was my second year, I had to go back to the training school to do advanced fitting. And I had to repair this component on an aircraft skin. And as I was riveting it, I had to do a countersunk holes for the rivets and so on, and do riveting. I had gouged the side of the skin slightly. Pure laziness to some extent, and clumsiness on my part. And it was, the supervisor saw it, brought me into the office to meet the chief training coordinator, and eat the face off me. How would you like to fly on a plane with that kind of workmanship, where the side of the skin of the aircraft has been scored? And he really meant it. This was not, this was serious offence that I had committed, and he brought me in. Well, it hit me like a ton of bricks, and I was about 17 at the time. I'll tell you the man's name. I hope he's still alive. I don't know, Wesley Black. But it was a fantastic training experience to have that at such a young age, to be told, you know, the seriousness of the work that you're doing. Now, I never did become a tradesperson. I moved into the technical staff at the age of about 19, about 18 and a half, from the shop floor, because I kept studying exams and moving up. But that discipline was instilled in us from a very young age, to be, it's a culture of excellence, and a culture where every tolerance and exact specifications, and that's what's throughout the aerospace industry, simply because of the nature of the industry. And that's what we talk about in this particular this section. And Mod 10 will talk about airworthiness. I'm probably going to get a specialist in to actually discuss airworthiness. It's not a field that I actually worked in, though I had to obviously work with regulations, work with procedures, precise procedures and so on, driven by these regulations. But there are people that are just specialize on airworthiness in aerospace companies. This is what they do their whole life. And their job is to assure the regulatory authorities, the Federal Aviation Authority, Civil Aviation Authority, that the company's products and processes are fit for purpose. And then we'll talk about, I'll probably bring in also a human resource, a former maybe vice president of aerospace, to talk about the culture, the unions, the leadership characteristics of the company. And I have experience with that. The unions in some of these companies are very fierce, very strong, and they're there for a reason, and one has to be able to understand that role if you're going to work in engineering and operational management. And then I'll talk here more about how you actually manage aerospace innovation and change. Now that is the subject matter of the whole of APS-1012, which is generic for all industries. But this is going to focus specifically on aerospace, and I'm going to talk about my personal experiences in the aerospace industry managing large-scale complex change. I'll be talking about it all the way through, but I'll talk about the actual process of innovation and change, or business transformation. Sorry, just to finish here, projects. This is Mod 13 is your projects. This is where the student teams who will be working in industry, and there will be theoretical student teams as well who won't be working on industry-based work, but they'll also be producing presentations and reports. So let's get into it quite fast. I'll tell you more about this. This is my education. This is the British system of apprenticeship. So they have two routes. You've got this academic route, and you've got this apprenticeship route to education and training. So these levels, a level 8 in the academic side would be a PhD, a level 7 would be a master's degree, or you can also qualify through a group called the City and Guilds. At level 7 you can do examinations there that are equivalent to master's degree. They're not university based though. And level 6 is an honours degree. Level 5 would be foundation degree or a higher national diploma. This would be equivalent to a technologist in Canada and the United States. And so over here you have apprenticeships. So simultaneously to this you could have a trade apprenticeship where you become a plumber, a fitter, a tool maker, electrician, and so on. Or you can move into becoming an engineering tech, an engineering technician. Therefore you have to have a higher level of academic. So you're working, as you're working, you're also studying academics. These higher apprenticeships for level 4, 5, and 6, these would be higher technician apprenticeships, or what would be called technologist in North America. And these are the kind of academic, and I went through this route here, well, both sides. So both this and this, all the way to this. So this would be equivalent, this is the industry equivalent, like a fellowship at City and Guilds. It would be the industry equivalent to a PhD, which would be a research path. This would be an industry path where you're becoming a senior executive. So this is all very formally recognized in the UK. This is a pure, so to get to these levels, you do have to achieve these levels of academia. So you cannot become an incorporated engineer if you don't have an engineering degree. You cannot become a chartered engineer if you don't have a master's of engineering degree. You cannot achieve fellowship of something like the City and Guilds Institute or other institutes unless you have done exemplary achievements in industry at very senior levels of management. The PhD is a pure research path and is a university based, but they have this mapping of these levels of achievement. Again, that's a purely academic, and that's a vocational, but it's built on academic achievement also. You have to have both. Anyway, I'll talk about that as we move forward in the course. This is some of the projects that I've particularly worked on. My real industry, aerospace industry pedigree in the management consulting field was between 1988 and 2006. By about 2000, I had already moved into many other industry sectors. And in the early 80s, I also worked in pharmaceutical food companies when I was at KPMG. But by about 2000, I started to involve myself in the machine tool industry, food industry, newspaper industry, and other smaller tier companies. But between 88 and 2006, it was these big companies that I worked at: McDonnell Douglas, Messier Dowdy, Toronto, British Aerospace, Boeing, de Havilland, Bombardier, Lockheed Martin, Magellan, so on. And I'll go through these more in depth with you. So this is the APS 101-2. I'm not going to go through it in depth, but this course again deals with the management of innovation. This is applying innovation. This is where you actually go into industry, and these are the different modules. These are more hands-on, learning you to be more effective in the workplace in terms of working in teams and being creative. This is the operations management. You take this course, you learn how to use operational thinking across any industry. So you go into hospitals, banks, universities, government operations, or any manufacturing company, from the chemical industry, the oil industry, aerospace, automotive. So these are common principles of operations across all industry sectors. And this is another course I teach more for the reflective engineer, history and philosophy. And really the purpose of this course is just to make you stand outside the box that you're in as an engineer and say, hey, what am I doing? Who are engineers? Why do they think the way they think? What's the history of engineering? How did engineering itself as a professionalize? Why is a British engineer trained differently than Canadian? And how is the profession governed in the UK versus the United States versus Germany versus France versus Canada? And they're all very different. So they create a different culture of engineer. So that's more reflective. And then this is the undergraduate course. This is what I'd call the mini MBA. And now for the course for this book, I haven't completely finished researching what books we'll require. By the time you watch this video, I will have sourced more books that you can look up. But I have already sourced many academic papers for aerospace operations and engineering management, and they're all uploaded onto the website. But this book here, these are my books. This book here, Sustaining Innovation Through Problem Solving, this is a book that is really APS 101-3, the Applied Innovation course, is designed around. Touches on, the course APS 101-2 touches it a little, but this is the core book for APS 101-3. So similarly, because you're going to be working inside aerospace companies, this book will help you. If you don't already have it, this will help you engage with the client, what I can't call them clients because they're not paying us, but industrial partners. But this book really focuses, is a real detail on the part 2 of this course, the engineering and product development section. And this book really is that part of the course is designed around this book. There's no doubt about it. I have other books coming out, new books, and I've also other guidebooks on transformation in the aerospace industry and also basically the lean enterprise. I have a guidebook on that, and I'll be releasing components of it throughout the different modules. So this book here, So this is the layout of it. I'm not going to go through it. You can read it. And I'll be filling this in later. I always show this at the beginning of all my courses. My job with you in work, in these jobs, is not to send you out with a bunch of formulas and equations and algorithms and that kind of thinking. It's to teach you strategic thinking. It's to teach you the thinking. So in this case, it's to teach you how to work as an executive or as a middle manager or as even a junior manager or a junior engineer in aerospace. So how do they think? So it's higher order thinking skills. That's what these courses are all about. To teach you how to think, to teach you to know what you don't know. Because you certainly don't learn it in the typical undergraduate engineering courses because they're so top heavy with technical subjects. So it takes you a long time, and employers are complaining at the lack of what's called the soft skills, which are really thinking skills, the ability to engage in the workplace, to know what's going on in a sensible way. So I'm trying to teach here from lower order thinking skills where you're just remembering equations and learn to pass exams, to how to evaluate, how to synthesize, and above all, how to create. Bloom and Anderson are, Professor Bloom, Professor Anderson are two American pedagogy, educational professors. So they teach pedagogy, they teach the theory of teaching, the theory of education. So they specialize in that, and they came up with this model, and I like these models. And so this is higher order thinking. So from being analytical, be able to synthesize across many systems, then evaluate, say, yes, this business is not fit for purpose, or this building is not fit for purpose. It needs new structures. You need to see the whole systems approach. And here at the higher level, Anderson goes one step beyond Bloom, and that is this creativity. Creativity is really the ultimate of thought, where you come up with whole new ideas, out of the box thinking, new ways of seeing the world, new ways of seeing products, new ways of seeing processes, new ways of inventing solutions that have never been. Steve Jobs is a classic example of a highly creative person, and Elon Musk as well with his ventures. Okay, so let's go through. We're going to go through these modules. I won't try to dwell too long on them. But number one, Mod 1 is Aerospace Industry and Context. So I talk a little bit about history, all the way back to the Greeks and some of the mythologies and so on about flying. And then the 1912, the biplanes, these were this is the British actually, you can see the symbol there. That's a British military plane. To the rockets, space shuttle, and then our massive military industrial complex with these B-1 bomber, stealth fighters, stealth bombers. This is all part of our history, and I talk about that. I give you pretty much a wide sweep of 2,000 years of history in aviation. Yes, you might be surprised that aviation was conceptualized way, way back with the Greeks. Everybody wanted to put wings and fly like the birds and so on. It wasn't until the 1700s, Sir George Cayley, out of the UK, London, England, who conceptualized the different forces of flight, lift and drag, stability, roll, yaw, pitch, and so on, that he conceptualized these aerodynamic principles that are still with us today. Also, Leonardo da Vinci, of course, he drew helicopters, he drew all kinds of planes in the 1500s, or I think it was the could have been the 15th century, 1400s, but conceptualized these principles that are all with us today, 500 years later. So these were very far-reaching thinkers, and it does us well to understand that, like all these airplanes, which really have only been born in the last 100 years, that these ideas had been there 400 or 500 years ago, and in fact the concepts were there 2,000 years ago. The reason I want you to, that's the innovation side, I want you to realize that so that you can think about, well, what's the possibilities for 50, 100, 300 years. Also, don't want to be naive. You need to understand that behind aviation and the world of aerospace is this military industrial complex, and it is mighty. It drives world's economy in some ways. And for that, you've got all these global hotspots. So you want to ask yourself, well, why are these global hotspots there? Well, they're big money for the military-industrial complex. So all this stuff that's going on in Syria and Iraq, North Korea, Afghanistan, Pakistan border, Ukraine, and its sort of business with the Russians, and in the Baltic states, Lithuania, Latvia, there's always tension there. The United States is putting all kinds of military bases around Europe, all bordering Russia. And of course, they're saying that the missiles and the military stuff that they're not pointed at Russia, but of course, that can be changed overnight. But you've all these hotspots. You have Mexico border here. Okay, so that requires military industrial not so much aircraft, but it does require helicopters. We need a lot more helicopters. We got to build helicopters to patrol this border. That's money for someone. Libya, Egypt. Bottom line is, I do want to put the military industrial complex in context with world affairs and world events and the political, social political side. Because I don't want you getting in there thinking like technicians. I want you to think like strategic engineers that think strategically. They understand what's driving these industries, what's driving them, what's the bigger picture. Not just getting in with a bunch of technical stuff in your head. So the other global aerospace, there's market drivers. Where's the markets? Where's the growth markets? Where markets are declining? What do customers want? What are the cost drivers? You know, the more oil goes up, the more petroleum, gasoline goes up, gas prices go up, airlines can't afford to pay for some, to make money on their planes because the economy's affected. So you're going to have to find ways of reducing the fuel costs of an airplane by making the airplane lighter. And so the cost driver creates lighter materials, composite materials, lighter airplane, less fuel to drive it, propulsion, basic force equals mass times acceleration and so on. These basic physical laws all drive costs, all these physical principles. So the lighter the aircraft, the less fuel you require, the less propulsion, therefore you save money. Government drivers, regulation and so on, or the need for war. Competitive drivers, if the Japanese built your wing for you for 15, 20 years, don't be surprised if in another 5 or 10 years they start building whole aircraft to compete with you. And same with Russia. You can go and you can think you're providing cheap labor to build your components of your aircraft, but don't be surprised if 10, 15 years time, you don't suddenly see an aircraft flying in the sky from some of these countries and it's similar to yours. So these are some of the global drivers, and you need to put that in context. Oh, for example, the Bombardier C series, the whole idea of it was to enter into the low end of the Boeing Airbus marketplace. Boeing Airbus did not like it. So what did they do? They reduced the cost of their aircraft where C series would compete, Bombardier C series, therefore keeping it out of the marketplace. And so there's been big problems with that aircraft program. And misjudging the market, misjudging it on behalf of Bombardier. And that's still all unfolding as this video is being made. Now, I also will talk about an example of British BAE Systems, formerly British Aerospace. This is the defense side of it. And they have defense products in air, sea, land, also communication systems, and they've support solutions as well, electronic telecommunications systems for military. And so they're involved, big conglomerate in this, and they're rivals, but they're also partners to companies like Lockheed Martin and Boeing and Northrop and General Dynamics and Raytheon and so on. And I did a lot of work with these companies, so I provide a little case study here just at the very beginning to set a context for the kind of work that I had done, and also work that this course is based and built on. Then I talk about, in Module 1, I put this whole aeronautics concept, so talk about lift and drag and the role of pressure, higher pressure, lower pressure. So the higher pressure here, pressure diverted by slower moving air, creates pressure exerted by faster moving air is higher here, so it lifts, forces the lift. And then I talk about the different components of an aircraft and also the movement about an axis, the pitch, The aircraft goes down or rises, lifts, or the yaw where it goes to the left or goes to the right, or it rolls where the wing goes up and it goes, it starts flying like this. So I talk about all those components because when you go inside an aircraft company, whether it's a airframe manufacturer or even a landing gear company or a company that makes engines, propulsion systems, you better understand the language and some of the basic physics. Some of you will really understand this at a very advanced mathematical level. Others will know nothing. But when you're walking through a factory and you're in an assembly area and you see a big aileron for the aircraft, for the F-15, you won't be getting into military companies, but if you saw a particular aileron of the fuselage for the Q400, Dash 8-400 or Bombardier aircraft, you'll actually realize, okay, so I know what that's for, I know its purpose. So that's what I talk about in this. Okay, Module 2, Aerospace Strategic Issues and Supply Chain. So this is the Boeing 787. These are all the partners. And I look at all the companies. In the United States alone, there's Boeing, there's Vought, Spirit, General Electric, Goodrich, Canada. You have Boeing Canada, Messier, Dowdy, Bugatti, now called Safran. In Australia, you have Boeing Australia. In Japan, you have Kawasaki, Mitsubishi, Fuji. In Europe, again, Messier, Dowdy in Gloucester, England, or it could be in Paris. Rolls-Royce in England, Alenia in Italy, and Saab in Sweden. These are all part of the supply chain, so it's a very vast supply chain. These are all the different components: the wings, the trailing edge. The wing is in Japan. The trailing edge is Japan. The Korea is the wing tips. The tail fin is in Washington, D.C. The passenger entry doors in France. The center fuselage in Italy. Forward fuselage in Japan. Forward fuselage, this one here in Wichita. The Rolls-Royce Derby, England, are their engines, jet engines. Gloucester, this is the Messier Dowdy Gloucester for the landing gear. Look at all these components. It's amazing. This is a big, complex supply chain around the world, and there's been thought given, intense thought about who these vendors are, how Boeing selected them, the criteria by which they selected them, the science of selecting them. You'll learn all these different aspects. That this is all part of a lean philosophy that was born in the aerospace industry in the 1990s. No longer did companies like Boeing, tier one integrators, systems integrators, build everything themselves, do it all themselves. So they realized that creating a global network of suppliers and so on, and certifying them and making sure they were fit for purpose and building long-term relationships was the best economic solution. This is just another slide that talks about the past platforms where the OEM had multiple tons of suppliers. Now there's a lot of suppliers here, but these are the big hitters and it's quite manageable. Maybe 20 to 30 major tier 2 suppliers is better than 200 tier 2 suppliers. So in the old days, the past platforms, the old days mean only like 15, 20 years ago, you had multiple suppliers, maybe 200 or 300, where the present platform, these are called preferred suppliers. And then in the near future, which is now actually from when this diagram was produced, system integration, full value proposition suppliers, that's these. This is the sample of that. So this went through, I want you to know this went through a metamorphosis or an evolution from this model of multiple suppliers to a model where you had highly preferred full systems, full value proposition. In other words, these suppliers are part of the value proposition and they're also sharing the risk. So it's not just buying something, they also are going to be, these suppliers here are risking as well because, well, they're given long-term contracts. This diagram up here basically shows you've got tier 1, you've got the original equipment. Here's the tier 1 suppliers for structures, propulsion systems, flight systems, navigation systems, fuel systems. Tier 2, they would actually produce the hydraulic pumps, the motors, the controls in tier 3, the piston rings, the O-rings for these tier 2 suppliers. So there's a hierarchy of suppliers, but the focus of these tier 1 is with the OEM. The OEM doesn't typically want to deal with the tier 2 and 3 suppliers. They're going to put their all their eggs in this basket here and assume that they're going to do well with their suppliers. They haven't time to run around looking through their tier 2 and 3 suppliers. lean aerospace. I just want you to know that as a result of the automotive industry's transformation in the United States particularly, and the rest of the world, Western world, in the 1990s and 2000s, by the early 90s, lean thinking, as a result of Japanese management techniques, which were originally American, by the way, from Dr. Duran and Edward Deming. Read about them, they're the TQM revolution, and it was Americans actually got the Japanese to adapt these principles when they were actually rejected by their home country automotive suppliers in the 1950s. The Japanese, after the war, they had only one way to go, and that was up, and they took all the help they could get from foreign engineers and specialists like Dr. Edward Deming and Duran, and they adapted all these techniques that these total quality management gurus and statisticians and mathematicians and mechanical engineers had developed, and created this whole concept of lean, the lean Toyota lean system, and that itself transformed the world of manufacturing. And that found its way into aerospace in the early 1990s. And in fact, in the late 80s, I worked at McDonnell Douglas, and what we had put together, what we call a total quality management system. And really what it was the foundation for what became lean, the Lean Enterprise Initiative. And that enterprise initiative was at MIT. Now, one of the things I always used in my work was the concept of an integrated enterprise, a holistic view of the enterprise. And I basically said you cannot make changes in an enterprise business processes unless you consider the people and the culture, and you also integrate the technology. So new software impacts the way workflows, impacts the new technology and new processes that you're designing. And it also impacts the teams, the way the teams work, and the physical layout of the workflow through the factory and the workflow through the offices. So I created this integrated enterprise model as a way of conceptualizing transformational change. And I'll talk about that in more depth. This is the actual lean aerospace study that was done through the 90s and has caused huge changes in aerospace today. And so the words and the language that came out of this are used in everyday living or in aerospace companies. Lean thinking, lean management, lean engineering, lean manufacturing is a way of life in aerospace companies today. So there was a lean aerospace initiative study that was done. All of it was done by a mixture of MIT, industry and government, and they created this lean enterprise model, and they used focus groups from across industry over a 5 to 7 year period. And what's remarkable about it is the work that I was involved with at McDonnell Douglas St. Louis on the F-15, F-18 programs. That work, that material that we generated was remarkably similar to the work that was delivered by MIT and this Lean Aerospace Initiative group. So they basically created best practice and benchmarks and metrics and so on for training so that they could transform the whole aerospace industry in the United States and anywhere else who wanted to use it. So lean enterprise thinking, again, from World War II, there were 3 major changes in thinking and of management. The craft era, mass production era, and the lean thinking era. So mass production really was born in the 1920s with the automotive sector. The craft era still remained actually in Britain well into the 1960s, 70s and 80s. They obviously did build cars and so on, but they stuck to their old technical craftsmanship, both as engineers and as trades, as opposed to the American mass production, simply because the American had a vast marketplace. But lean thinking changed everything. So the focus here in operation in craft is single items, mass production, batch and queuing, and in lean thinking it's synchronized flow in the pull system. So pulling the work, not pushing it through to reduce inventory. In quality integration, part of the craft, inspection a second stage of production, but in lean thinking there should be no inspection. If you design and build a product, you work and you make it right the first time. Right thinking the right way the first time. The business strategy was customization and the mass production economies of scale, so everybody got similar cars. But lean thinking is flexibility, adaptability, and what's now become agility, agile processes, and mass customization. So you're getting customization from that craft era and mass production. So lean is about mass customization. And then improvement, the master himself, the master craftsman driven, I can fix my own things. From an expert driven periodic improvement. So that was the rise of industrial engineering, who were really the efficiency experts. This was individuals do it themselves. This was industrial engineering, where you were training industrial engineers to come and do efficiency studies in the mass production era. But in lean thinking, the workers do it themselves. So you're instilling self-direction, problem-solving skills, and so on. Okay, so that's really the thinking. I'll go into it in more depth. Lean enterprise, just organizationally self-sustained state, quality of work life, continuous improvement without end, confidence to continuously redesign. In my book, and this is out of APS1013, you're going to have to learn some of these principles. You won't get into it to the depth you get into it in APS1013, but if you're going into a company to improve their processes, which I want you to do in this course, you're going to have to understand how to think about getting processes under control, how to improve them, how to problem solve. There is a problem solving process that's described in the book, from selecting issues to designing the process, confirming the process, and then doing root cause analysis, fishbone diagrams, cause and effect. I will teach you this basic, in fact I've got videos on it, but we can't spend a lot of time on this. You cannot perfect this as you would in APS 1013, but you do need to learn these principles in order to engage in the aerospace companies that we are working with. Module 4 is product development, okay? So the target typical aerospace companies, this is actually an excerpt from a benchmark study that was done with aerospace companies, and from Booz Allen and Hamilton, actually, the big defense consulting company. And the target at that time was 40% to 50% reduction in product development speed, time to market, 30 to 40% engineering productivity, Six Sigma, and reducing product cost. These are drivers inside engineering, where they do the design of the aircraft or the design of the weapons systems or whatever it happens to be. These are the kind of targets that management's looking for in order to be competitive. And so you've got all these best practices, and I have a whole methodology, which I'll only share some of it with you, but it looks at how they do their engineering and product development process. You're going to learn that, how Bombardier does it, how Lockheed did it, British Aerospace, Messier Dowdy. How you do requirements generation, how do you actually define what the customer requires in aerospace? How do you put teams together, integrated product teams, cross-functional teams to actually work on it? So what I was looking, you have to be best practices here. So I'm looking at particular companies, and I'd go in and assess them, and I'd tell them, as far as engineering procurement interface, you're weak compared to this company. Your internal design reviews are good, they're strong, or they're not strong. Your engineering tools are strong, or they're not strong. How you verify designs are strong or not strong. How you design the cost and value. So these are the different best practice areas. So this is an assessment tool that we go into, and we look at an engineering operation and we say, yeah, you're fit for purpose, or no, you can improve how you perform. And there's a whole approach to that, the scoping out the different areas of the business, the 15 best practices, gather data and then assess. And then give them a feedback. So this is something that I've done in many companies using a methodology which allows me to judge their capabilities in the worldwide marketplace. And this is an example of, for example, requirements generation. This is where they've minimal capability. This is where they're world class. This is where they're best in their class. So if it's a landing gear company, then this particular company on this occasion is a best in class when it came to requirements definition. But in minimizing changes to requirements, not very good at all here in the marginal. They're marginal in terms of it. So it says they have some ability to maintain freeze points. That's freezing the design. And they require changes. Requirements change drives substantial rework. That's not a good thing. But what you want to be is up here. Strong process ability to limit unjustified change. Change control board with customer representatives. So you got the customer involved. And customer churn causes no significant rework. That means that people are turning in the customer. You're not getting constant rework because there's very there's very precise rules around change, managing change, and customers changing their minds. So this is a whole matrix that shows how a company performs among these dimensions. This happens to be requirements generation, and then there's these subsets. So given that there's about 15 here and maybe 10 subsets, that's like 150 different dimensions that we analyze in a company and tell them this is how good you are in terms of best practices. Now in the book I talk about these different bodies of knowledge: integrated product development, that's cross-functional teams working together; the body of knowledge called project management, PMP, or program management; and body of knowledge called business process management, that's the undergrad course I teach; and then this organizational change and political management, APS1012 talks about a lot of that; and then product data management is a software package to manage data. And this whole concept of systems thinking, so there is an institute for systems engineering, there's a whole body of knowledge on systems engineering. All these components are required to efficiently manage integrated design, engineering, and manufacturing operations. I call that the holistic view. This is another way of looking at it. But the most important of all these bodies of knowledge is process management, because it cuts across all of them, ties them all together. Not project management, process management. You need an integrated enterprise architecture in which to manage the process. Here's an example. So instead of looking at the organization as just who reports to who, you look at it where work gets done. So the very top level is strategic management processes. Then you have operational management. Your core business processes, you acquire business, typically called marketing. You define the product, that's product engineering, manufacturing engineering. As you define the product, you define the process. And then you build it. This is the big factories. So if you go to Bombardier Aerospace, there's about 11 or 12 bays in Downsview here in Toronto. And that's where they've got materials and the production system, big fuselages and all, and wings are being attached, and massive factories the size of football fields. Boeing's is a vast out in Everett in Washington, the state of Washington. So, and then ultimately you've got support. You support the customer, salespeople, distribution systems, customer service, and spare parts. Then you have these support systems: industrial engineering, performance management, human resources, and information technology. Typically a group called IT. And this is the breakdown of those processes and functions, all the components. I won't go into them here, but if you look at these business processes, these are the sub-processes and the knowledge areas that one requires in order to design and build these business processes. So it's a big area. I also will introduce you to a modeling tool I use to model the whole enterprise of aerospace companies called IDEF, Information Definition Modeling Technique. IDEF A0 is the functional one. So it's a parent-child. So this particular process, it's assemble widgets, is made up of these 3 sub-processes, and then this process is made up of these 4 sub-processes. So this is the parent, this is the child. The breakup of these 3 that's the parent, and then this particular sub-process, that's the child of them. So as you decompose it, at the time you get to this level, you're dealing with individual pieces of work that individuals are doing. So in this case, is establishing customer requirements, then designing the system. This is a big look at it, and then building the system. So here's the needs from the customer expectations. The output is understanding the customer requirements. The input to this next process, designing the system, is those customer requirements. Then you consider alternative technologies going in, the knowledge from previous designs going in. The output is a design. And then the raw materials go to the manufacturing system, and out of it comes a product. So this is the way the IDEF modeling tool, and I use that in order to model whole aerospace enterprises and document all their sub-processes and sub-processes, and I'll share that with you. And this is an actual example of, after doing this, actually designing a business process architecture. And this is the conduct strategic management, this is program management, this is the core business process where you have customers, suppliers. So that you acquire customers, suppliers also produce materials for the building of it. So you notice I don't say marketing here, I don't say engineering here, I don't say manufacturing, because they're all working in cross-functional teams. You need engineers and manufacturing people to be upfront talking about the customer requirements to assure that you actually can deliver. You can't think the salespeople and marketing people can deliver those requirements for a certain cost. So you include people from the downstream in the upfront processes. So it's process-driven, process thinking, not functional thinking. This is an example actually from Bombardier. This was the very, very first draft of stage one thinking about how their phases of product development occurred. So concept definition into review, preliminary definition, detailed definition, and these were the milestones here. So they had milestone meetings. So then these were the sub-processes of that particular process. But we realized this is not how things are really done in the real world. They don't do all these processes, have a review, then go to the next phase. There's a lot of overlap between these phases. You don't just stop, as they're doing the concept design, they don't finish the very last piece of the concept design before they start getting management approval or doing preliminary design. So the next stage of thinking was more practical, where concept design, preliminary design cut across, started more in the concept design, so they took a risk here before you made a decision to move forward, so that you could speed up the work, speed up the decisions. Similarly, when you do testing, you don't do testing at the very end here. There's testing happening all the way through. So you're doing early testing even at the design stage, building test rigs. So we realized this approach where processes weren't happening in between milestones, they were happening across milestones. And you're inheriting risk, but you're also you're managing that risk of bringing work up front with, you've got experiential judgment, but also you're reducing the lead time. You're reducing the time to market. So you're also keeping a lot of these people busy that are working in this by getting them to start ahead into the preliminary definition. You see it here. I'll talk about all this in the class. This is another schema where to teach enterprise process thinking, you've got this level 0 process, acquire, define, build, support, and then the product development breaks down into, was Lockheed schema that I did. So then I said that this is you've just seen this, these are the cross-functional processes, those are the milestones. So then we took one of those processes and break it down into what are the databases that support it and what sub-processes are required. So these are the sub-processes, you get inputs into those and outputs. And then the level 4 processes relate to each, this was this Lockheed engineering procedures. I'm not going to get into that in this particular, I'll actually show you in the class, but essentially you had these functional processes and the gates, these milestones, and you had produced deliverables, and you had to make sure that they were aligned, each of the deliverables from the different groups was aligned so that you could go to the next gate. That's the stage gate process. This is an example of cross-functional teams. I'll just fix this here. Sorry about that. So what this is telling you is you're going from people sitting in different cubicles. You notice here, manufacturing engineering is this cubicle, operations is in here, finance is here, engineering, materials, all sitting in different cubicles. Now they're all working on, these are the aircraft program, these are the metrics and so on. So you organize location of processes, communications and so on. So this is co-location, it's an IPT. It's around the functions. So you've got cross-functional, communication is cross-functional, the focus is for a program, the tools are functional. But when you go to a process-centric, the evolving future, when you have tools, virtual product development tools, and you form true IPTs, there's no concept of these different departments. So what you have is a virtual team. You can actually work, you can be anywhere in the world because of all these suppliers. We talked about that earlier. So using virtual product development, You can have product, you focus on product definition, product integration. Notice we don't talk about the functions, we focus around the actual business process issues that we are working on. And we're using a virtual team. Formality, the IPT is very formal, and they drop their functional hat and they focus on the team hat. And they're focused on the customer needs and so on. Number 5 is the Aerospace Program Office. This is just the roles, how the business is organized for programs, team behaviors, top level phases, gateways, key milestones. That comes from the business process, so that's how they manage. The Program Office, they administer, they govern all these milestones. This is an example. This one happens to be from a landing gear company. This is the Airbus program. This is the Boeing and military. Actually, this is the Airbus business unit. This is the Boeing military business unit. This is the regional aircraft business unit. This could be the Bombardier. This could be for Cessna. This is Boeing military. Could be for the F-15. This could be for the F-18. This could be for the Apache helicopter. This particular business, the Airbus. This is the A380, A330, and so on. So this company's program, they have many products that they deliver to these different programs for these industry tier 1 suppliers, the OEMs. So this is the Airbus. So obviously you would want to organize your business around the Airbus group, because the Airbus corporate they care about their programs. They don't care how Boeing's doing, but they care about their programs. So it's best to have a business unit focused on what you sell across these programs to that business unit. These are the internal functions of your company, because they're going to work on IPTs, cross-functional, in these programs. So this is the schema of how a program management office would be set up across the whole business, and then you'd have sub-offices on each of these programs. So this is the big picture, and an executive committee. So these are very senior vice presidents that are making sure these big customers are satisfied and are happy. It's a big job, and people typically, there's usually a big vice president for programs, a senior vice president, like up there with the president of a big aerospace company. So if you look at any major supplier, tier 2 supplier for landing gear or for Rolls-Royce for engines and so on, this is the kind of scope, and you would have thousands and thousands of people in each of these programs, by the way. So you may have 30,000 people on the payroll just for these. You may have 10,000 just working on the Airbus business. You may have another 10,000 on Boeing. So all this has to be managed. This is more detail. How you create work packages for the note. This one here is program the commercial. It's the business unit here could be Boeing, and then you have commercial, not the military. And then you have the nose landing gear team, and you have the main landing gear team. And then here's the work packages, and here's the various cross-functional teams. You have a chief engineer for that particular program. So all this has to be managed. That's what the program management office does. And then you're using that phase milestone process. So this happens to be, again, landing gear. So in this phase A is business development, phase B business capture, phase C preliminary definition, phase D detailed design, phase E validation, and then these are mini milestones. And this is the bigger picture phases. Each phase is characterized by different processes, deliverables, and so on. Program management is all about it's basic principles of project management. Plan, do, check, react or act, and communicate and deliver. So it's basically the cycle. You're always asking these questions across all these programs here, these work packages, using the process architecture to make decisions, and using these basic questions over and over again. Aerospace program initiation execution. So if you go back here, these are the work packages. Okay, so this is the early stages of executing. So you're set up your office, you have the governance, you know how you're organizing your different programs, you know how you're going to monitor them, collect costs, the timing, the cost, the quality, the schedule. So how do you execute it? Again, this is in the book. But you have to have budgets, deliverables, quality reviews, so you have to set up your reviews, when you review them. This is all about using the business process architecture to actually manage and execute a program, run IPTs, manage risk from phase to phase. So you have to have these work packages, and a deliverables architecture. So this, for example, the part definition is made up of a 3D model, structural sizing. That part definition and manufacturing data, that's the machine tool setup drawings, the feeds, the speeds, the work measurement data goes to the manufacturing data. So the part definition plus manufacturing data, including the tooling data here, would give you the detailed product data. So that's your customer deliverable, that's your key sub-deliverable. So there's an architecture of deliverables that you have to track. And we'll get into that. I have lots of examples. This is a work planning template. So this happens to be D4.2.1, develop detailed design layouts. So these are all the sub-processes: identify information, evaluate design alternatives, design layout alternatives, develop interface layouts, perform internal systems analysis. So this is the estimate of the time, the hours. It's a designer required, that's the skill. So you get these work planning templates that allows you then to define how much time it takes for individuals to do work. This is all basic project management approach. This is an example of a cross-functional process architecture. So you have to have all the sub-processes for each of these main processes defined, so then you can create work planning templates for each of them. So it's just an example of how you model an enterprise down to the detail, and it's these where the work gets done. It's this where the program management is actually tracking. When did they do the main assemblies? Did they generate have they developed the sub-assemblies? Have they created the electrical design done, and so on? This is an example of swim lanes, again, all from business process management. So mechanical design, as you go back here and see these different components, P2.1, P2.2, P4.1. So these are the different deliverables. So that mechanical, these are the functions. Mechanical design produce these deliverables, and electrical design produce these. And this is for the defined subcomponents of this particular subsystem. Okay, so we go into that kind of detail in Module 6. Program execution. Aerospace, so enterprise management systems. Now we're looking at the manufacturing operations. Well, it's manufacturing, but it's also looking at how data across the whole enterprise is managed. So an ERP, an enterprise, optimizing the total enterprise. So here you have the various functions: engineering, product support, payroll, finance, services. And these are existing silos. So these are the existing siloed organization, but your idea is to create an integrated process like that integrated enterprise, like the business process architecture. So typically you have these functional silos in companies. You've got also, in this dimension, you've got customers, you've got suppliers, and within your own company you have multiple divisions. You have the military division, you have a commercial division, you've got overseas groups. All that information has to be optimized. How do you do it? Well, we get back to those core business processes of win a program, acquire business, design the product, build it, support it. So you're starting to do process thinking, your core processes. The idea is that you use the legacy systems. Don't worry about these words here, but basically you want to create, you're going to buy a whole off-the-shelf package like an SAP system or a BAN system, but you're going to have to also migrate from your legacies, your current systems, into this new integrated enterprise software package. So we'll talk about that and give some case studies. There is a formal approach to doing systems development. I'm only going to touch on it, but I want you to know when you're implementing, and it happens all the time in aerospace companies, new software packages are brought in. There's a whole systems approach to doing it. It's a science. You define your business strategy, you justify the new system, you do the requirements definition, you send it out for tender to a outside vendor, you do systems design and development once you've acquired it, systems implementation, and then evaluation. And there's this whole approach has been systemized and so on. I'm only adding that in case the project that you're working on has a software package associated with, an ERP system associated with it. But it is something you ought to learn if you're going to work in engineering or product development operations or manufacturing operations in an aerospace company. You need to understand ERP, because that's the software system that drives master scheduling, material planning, shop floor control, the finance system, human resource system, and the customer relationship management system. It's all tied in, so you need to learn about that, and that's the purpose of this module. That's just the approach, how you go about implementing these systems. Okay, Module 8, Product Data Management. As you go through the product development process, all the way through production planning, tool design, plant floor, quality assurance, you're generating data. Data has been generated and you have to capture it. So you can capture it obviously when you feed it back into the ERP system, but there's specific product development software developed for aerospace companies. These are the databases for manufacturing data, for engineering data, work in process data. So these databases require you to track all the data that was created, and also to track orders when you change the design of components and you send those engineering change notices to the shop floor. You have to assure yourself, first of all, that they got implemented properly. Number two, that the information was captured. You're bound to do that by the regulation authorities. They need to know they need to be able to be traceable. Every change on an aircraft program or an aerospace product program has to be trackable and traceable in case something goes wrong. So this is an example of the life cycle phases: concept, design, fabrication, assembly. Notice it's been shrunk, the time has been shrunk. But as the aircraft design goes through multiple changes. It doesn't just stay. It goes to, as you've got what you marketed it to the customer. This is as you've actually configured it, designed it, as configured, as designed, as built, as delivered, as maintained. How you build it, because you find problems with the design, you've got to capture that information, because it may not be as you designed it. It won't be major changes, but there will be changes in how you design the doors, the landing gear doors, the flaps of the aircraft, slight changes, because you find snags on the shop floor, you find snags in the manufacturing process. So all this information has to be captured. Product data management software, look it up, has these major issues: data vault and document management, data warehousing, ability to do data mining, ability to do AI, artificial intelligence retrieval, then group technology, parts coding, then you have your product structure, workflow management, and project management. These are all part of the PDM system. Manufacturing planning and control. This is really deals with the factory operations. So you start off with business planning. It talks about your sales and profits. Then quarterly planning. Talk about what aircraft you get out the door that quarter. So that's your product families, 400, Dash 8 400, Dash 8 300, Challenger aircraft, whatever it happens to be. And then you do your monthly, which is your master scheduling, your models, and your options and accessories, and so on, for a particular variation of a particular product or a particular aircraft. Then your weekly is your material and capacity planning, and then you find out. So you have a hierarchy of planning and control needs. So this is the shop floor on the line here, and this would be middle managers managing inventory and so on. This model has been around. It's a proven model, a proven approach. It's been around since the late 70s and 80s. Its software packages are still configured around this. I'm going to show you examples of how I've mapped business processes to software packages to teach you how software and business processes are aligned, and how software actually drives business processes. And that's software was originally driven, the design of it was driven by business processes. But in modern times today, business processes are driven by software, how the software is configured. But basically, I'll go through this closed loop model. This is your top management planning, operations planning, and operations execution. This drives this and drives this. You have your database files here, which is in the product data management, the PDM system. You've bill of materials, you've inventory status and routings. Up here you have business plans, sales plans, and then actual production plans. How many aircraft a month? 5 aircraft a month we're going to produce. And are your resources and capacity okay? You ask that question. If it is, yes, master schedule. That's where you actually schedule end items, the actual aircraft itself, or the wings, or the components of it. Then you do the material planning, the subsets out of the bill of material. Then you do capacity planning from the routings. You know, what work centres do you have? How many hours do you have available? How do you know you have those hours? How accurate is it? You ask yourself, is the planning okay? If the planning is okay, you go and buy the raw materials or the purchase components. You then do shop floor control. You get the feedback from the shop. You've executed, you've released your work orders to the shop. And then you have these performance measures. So some of the work you guys are going to be doing will be inside companies, and we'll deal in this level here between master scheduling right down to performance measures. This is an example of a landing gear company. That's their main business processes, you see. And this is the inputs and outputs. I mapped them. And this is a very extensive bit of work that I did. And then I mapped those, I broke all these into their components, into the sub-processes underneath each of these mega processes. And then I mapped those needs to this software package master, which is basically this generic model. Was an actual software package from a company. And I documented that, and then I mapped, you notice, you see capacity planning here, material planning, master scheduling. You notice here, capacity planning, production planning, let's see what else there is. Material planning somewhere here. And what I did was I mapped these major business processes in the company. 1, plan for manufacture. 2, plan for production. 3, schedule the factory. 4, provide material. 5, convert material. 6, ship products. I then mapped those to the software that you see here. And we'll explain that. So that's sort of manufacturing planning and execution, how software is used, because you're going to be working with that as well. Module 10, we're moving into all this cultural stuff. This is the aviation and airworthiness. So it's about an acceptable level of safety, fit and safe for flight, technical and operationally airworthy, and the evidence of this effect. That's what airworthiness, that's what regulations want, safety and prove it. There's big agreements, we'll talk about these, between the United States and the European Union, FAA, CAA in Britain, and then the European Union itself. We talk a little bit about these relationships between the directors of flight standards and the European approval for standardization. Executive management, talk about how it's organized, bilateral oversight, a board of directors, certification oversight board, and then joint maintenance oversight board. It's all about oversight to assure themselves that these airworthiness procedures are being implemented. Next, we'll talk about aerospace culture. Remember, cultures, at the core of culture is the psychology of the individual, the psychology of the teams, and the psychology, or what we call the business psychology of the organization. So individual, teams, departments, and organization. And all of this starts with this whole concept of Maslow's hierarchy. So from the bottom, your concern is food and shelter. At the very top, ego, self-respect, but up here, self-actualization. So companies that actually have people that are working at these levels up here are actually going to be much, much more productive than if they're scrambling around down here trying to just make ends meet. This is just a fact of life. So the whole concept of business psychology is also about the quality of life. So we're going to talk about that in this section. And we'll talk about managing complexity, unions, and so on. Any change you bring into a company, and companies are under change all the time, you have so many different aspects to deal with. You have the actual implementation team, you got to deal with the unions when they make a change to processes or organizational issues, you got to deal with the unions. You have business process managers actually going to implement it. You've got the disciplines that are going to receive the new processes. You need an overarching steering committee. You have vendors for new software packages you're bringing in. Of course, you always have to include your customer, because if you're going to change your processes, it's going to impact their designs. You got to assure them everything's good. So also we're shifting from this control hierarchy model to a self-directed model. So from functional mechanistic thinking to business process and systems thinking. This cultural shift is still ongoing. We've been at it for 20, 25 years, but doesn't mean to say that all these companies practice this model. So culture matters, and culture, sometimes companies go through major transformational change programs over 5 years. If you walk back in 10 years later, they're back to the way they were 15 years prior. This happens. And it's because of change of leadership, what leadership must do to maintain change, what leadership must do to change a culture of self-direction and so on. Get the right graduates that can fit into these cultures that are self-directed and so on. So again, I'm going back to that original one, from sitting in cubicles, co-located, that's a good thing, but moving toward this cross-functional integrated project model. Nearly finished. And the last module is managing innovation and change. And I get back to that integrated enterprise approach. I'm going to take you through, and again, you'd learn this in more depth in APS 101-2 and APS 101-3, but I'm going to actually take you through some aerospace transformational programs that I worked on, and how because it's really a wrap-up of all the previous stuff you've learned. Because at the end of the day, the reason I'm putting this innovation and change at the very last piece is, if you do want to have a career in aerospace and you do want to become an executive, etc., you're going to be constantly changing. You're going to have to constantly improve the operation. So managing change, managing transformational change, disruptive change, is going to be a way of life. So you ought to actually know there is a science behind it, and I'm going to teach you that in Mod 12. Obviously, if you really want to be a practitioner, you need to get about 5 years experience in a big 6 consulting firm. And you could take my course and all the APS 101-2 and 101-3, and all that'll do is expose you to the basic principles of it. This will just give you a taste for it, but to know that you've got to learn this stuff if you want to be an executive working at senior levels of aerospace. There is a process to go through executive leadership. There's engagement mechanisms with people. Most of it's all psychology. Reinforcement mechanisms. It's like anybody, you want to change behaviors, you're going to have to model the behaviors, reinforce the good behaviors, punish the bad behaviors, and reward them with good behaviors, give them more money, and so on. So there's a whole systematized approach about this. There's these matrices, these stages of excellence. Rubrics, they're called in the university setting. We call them stages of excellence, from a traditional organization to a world-class, high-performance organization around strategy, how they measure, how they do business balance scorecard, how they develop their culture. So again, I'll take you through some measurement systems that we have to assess companies. And this is one of the measurement systems. How ready are they to change? How is the change program well structured? And I've done this in aerospace companies, and I'll take you through some case studies. How do they program, manage, and execution? You're going to learn that for aircraft programs, but it also applies to managing the change if you're transforming the enterprise. This is examples where a company, I would review a company, it's with a company 5 years prior. This is where the black represents where they were 5 years ago. And this is where they are today, or when I did this review. They'd improved their scope and alignment significantly. They'd improved their IT enablers significantly. Still very poor communications. They'd improved pretty much all governance much better. Their process sophistication had improved. Their financial performance everything was improved dramatically. But they still weren't world class. That's room for me to go in and help them become world class. That's the case for change. This is a strategic performance. You go from a mission all the way down to personal objectives. So mission, values, vision, strategy, balanced scorecard, all the way to personal objectives. So this is just a way to tie the company's goals to the transformational program. There's all kinds of reasons why people fail, why initiatives fail in aerospace. Not enough emphasis on people, the soft stuff, weak project management, lack of stakeholder agreement, and so on. So success depends on the people, the technology, and the organizational. This people is the psychological side. This one here. There's the change management curve on informed certainty. Informed certainty, this is the emotional ups and downs. And we'll go through this. Again, I cover this in great depth in the other APS programs, but you still have to know about it. So here's where basically the preparation phase for a change. This is the acceptance phase. This is where people are committed. By the time you implement like a new product development process, a new manufacturing process, a new customer relationship management process, you're successful when you know everybody's internalized it and they're following it. They don't even think twice about it. There's a whole methodology for achieving this, how you manage projects, what to do, how you manage change, how you do it, and then the actual change itself. Just to let you know, in Module 13, you're going to present your final projects. These are past projects from all across, these are past aerospace projects from all across my projects, my courses, sorry. And you can get that off my company website. The last one was Bombardier Aerospace C-Series problems. Lean aerospace, lean manufacturing in aerospace was one. Skylab failure, Apollo, Pratt & Whitney. So some of these were real on the job. Solar Ship, Messier, Dowdy, Pratt & Whitney's were actually work that people did inside these companies. Okay, that's it. Thank you very much.